Previously, we discovered the golden ratio and its appearance in nature and art. Now let's see how it relates to the Fibonacci sequence. First, we will find a continued fraction for phi equal to 1 plus the square root of 5 divided by 2 equal to 1.61803, etc. A continued fraction is a unique way to write a decimal in fraction form. With rational numbers, the continued fraction has a finite end, but with irrational numbers, the continued fraction has no end. To start, we take the integer part of phi and give it the notation a naught. So a naught is equal to 1. Next, we name phi 1 equal to 1 divided by phi minus a naught. And the first step in the continued fraction form of phi is written as phi equal to a naught plus 1 divided by phi 1. We can see why this works by just plugging in a naught and phi 1 and checking. Phi equal to a naught plus 1 divided by phi 1, which is equal to 1 plus 1 divided by the fraction 1 over phi minus 1, which is equal to 1 plus phi minus 1, which is equal to phi. However, when we calculate the value of phi 1, we notice something interesting. Phi 1 is equal to 1 divided by phi minus a naught, which is equal to 1 divided by 1 plus the square root of 5 divided by 2 minus 1, which is equal to 1 divided by the fraction negative 1 plus square root of 5 divided by 2, which is equal to 2 divided by negative 1 plus the square root of 5. When we rationalize the denominator by multiplying this fraction by 1 plus square root of 5 divided by 1 plus square root of 5, we get 2 plus 2 square root of 5 divided by negative 1 plus 5, which is equal to 2 plus 2 square root of 5 divided by 4, which is equal to 1 plus the square root of 5 divided by 2, which is phi. Thus, phi 1 is equal to phi. There is a sequence in finding terms in a continued fraction, and what we find is that all of the a sub n values are equal to 1, and all of the phi sub n values are equal to phi. What this gives us is one of the most boring continued fractions out there. Phi is equal to a naught plus the fraction 1 divided by a1 plus the fraction 1 divided by a2 plus the fraction etc., which is just equal to 1 plus the fraction 1 over 1 plus the fraction 1 over 1 plus, etc. So far there's nothing interesting to this pattern, but from this continued fraction we can calculate what are called convergents, which are obtained by only using a limited number of terms in the continued fraction. If we just use a naught, then phi is equal to a naught equal to 1, which we're going to write as 1 divided by 1. If we use a naught and a1, then phi is equal to a naught plus 1 divided by a1, which is equal to 1 plus 1 divided by 1, which is 2, and we will just write that as 2 divided by 1. Using a naught, a1, and a2, phi is equal to a naught plus 1 divided by a1 plus 1 divided by a2, which is equal to 1 plus 1 divided by 1 plus 1, which is equal to 1 plus a half or 3 halves. Following the same pattern, using a naught, a1, a2, and a3, we can say that phi is equal to 5/3. So by now we are starting to notice a pattern with the sequence of convergents in their relation to the Fibonacci sequence. The Fibonacci sequence is a recursive sequence where each number is found by adding the two previous numbers to it. It is defined by f1 equal f2 equal 1 and fn equal fn minus 1 plus fn minus 2 for n greater than or equal to 3. And we can write the first few terms as 1, 1, 2, 3, 5, 8, 13, 21, etc. If we look at the ratios of consecutive Fibonacci numbers, we get the convergence we just calculated and can easily write some more. 1 divided by 1, 2 divided by 1, 3 divided by 2, etc. So, the convergents of the golden ratio are ratios of Fibonacci numbers, which also means that the ratios of consecutive Fibonacci numbers are approximations of the golden ratio. And these approximations improve as we go further out in the sequence. We can see this by rewriting the sequence of convergence in decimal form. These ratios show up in music in the intervals between notes, and we can see all kinds of relations to the Fibonacci numbers. Here are a few basic intervals and what we can notice. Going from any note on a keyboard to the same note above or below is the interval of an octave. We can see the number 8 in the word octave, and that is a Fibonacci number. If we start at the note C on a piano, calling it note 1, and move up along the white keys, then the next C above is note 8. When we look at the frequencies of octaves, they form a ratio of 2:1, meaning the octave above has twice the frequency. If we start again at the note C, calling it note 1, and move along the white keys, the fifth white key we reach is G. We call the interval C to G a fifth, And again, we notice that 5 is a Fibonacci number. The ratio of frequencies for a fifth is 3 to 2. This means if we multiply the frequency of C by 3 and the frequency of G by 2, we get the same frequency. The interval C to A is a major sixth. While 6 is not a Fibonacci number, the ratio of frequencies is 5 to 3. This means if we multiply the frequency of C by 5 and the frequency of A by 3, we get the same frequency. The interval C to E is a major third. 3 is a Fibonacci number, but the ratio of frequencies is 5 to 4, which doesn't quite relate to the convergence we saw. However, we get a major chord C, E, G, C when we use the note numbers 1, 3, 5, 8, which are all Fibonacci numbers. There are different opinions about what intervals sound pleasing to the ear, similar to different opinions about what art is pleasing to the eye. With musical intervals, the differences become more apparent when we consider different tuning standards and music history. But similar to the golden ratio, we can see these ratios of consecutive Fibonacci numbers in the natural world. For example, in the spiral patterns of pine cones, the right hand and left hand spirals are often pairs of Fibonacci numbers. And in the solar system, there are spin-orbit resonances, which are ratios with small numerators and denominators. And some of these involve Fibonacci numbers. For example, our moon spins once around its axis for each rotation around the Earth, which is a 1-to-1 ratio. And Mercury spins on its axis 3 times for every 2 rotations around the Sun.